Throughout this entire lesson, we're going to be working on graphing a function by hand. And we're going to be working on the same function the whole time. So this is the function we're going to graph. F of x equals 2x squared plus 3 divided by the quantity x minus 1 over x plus 1. So hopefully you saw on the previous slide that there are kind of these steps you can follow to graph a function. And basically we're going to go through each of those steps one by one in each segment of the video, and then at the end Elizabeth will put everything together for you and we'll actually graph the function. Okay, so let's get started. So what's the first step? Okay, well the first suggested step is to determine the interval on which the function should be graphed. Okay, so this step doesn't really require much algebra, if any. Basically, you're just looking at your function, and sometimes you might be asked to graph only part of a function. For example, maybe you're given a polynomial like f of x equals x cubed plus 4x squared plus 7x minus 3, but you're only asked to graph it from 0 to infinity. Or sometimes maybe you're given a function that has a limited domain. So maybe some sort of natural log function or a shifted natural log function that only exists from like 0 to infinity. So sometimes you have a function like that. So this step is basically just telling you, take a look at your function, think about on what interval you're going to graph it. This kind of just helps you look forward to the next steps. Okay, so what about our function here? So we have a rational function, and on which interval are we going to graph this function? Well, rational functions are continuous everywhere except at values that make their denominator 0. So if I just glance at this function, I kind of see right off the bat that 1 and -1 are going to be discontinuities of this function. But besides that, I'm going to be graphing it everywhere. So we're going to graph this on the whole real number line, basically, right? So I'll just say we can graph for all real numbers but x equals 1 and x equals -1 will not be part of the domain. Okay, so this step is just meant to get you started thinking about the domain of the function, but we'll look at this more in depth in future steps. Okay, so let's move on to the next step. Step 2 of the graphing process is to check the function for symmetry. Okay, so checking for symmetry may be something that you haven't done in a long time. So we're going to take just a few minutes to review the types of symmetry that a function has and how to check for those. Okay, so a function can be even or odd. Those are types of symmetry. So first of all, even functions. Even functions are symmetric about the y-axis, and I'll show you a picture in just a second of that. And an even function has the property that f of -x equals f of x. Okay, so let me show you a very simple example of an even function and how it meets this property. Okay, so a very simple example of an even function is f of x equals x squared. Okay, so basically how this works, if I didn't know that x squared is even and I wanted to check that, I would figure out what f of -x was. Okay, and the way you do that is you just plug in -x for x and then simplify. Okay, and ultimately you're trying to see if you get f of x back out. And in this case, if I take a negative and square it, it becomes positive. So this simplifies to x squared, which was the original function, right? So I see that f of -x equals f of x, which tells me this is an even function. Okay, so what does the graph of x squared look like? Well, it's a parabola, right? So something like this. And we see that y-axis symmetry, right? So my picture, of course, isn't very good, but for a well-drawn parabola, x squared, you can just fold that over the y-axis, right? And it folds on top of itself. It's a mirror image on each side of the y-axis. So this is an example of an even function and how to check for an even function. Okay, so what about odd functions? Well, odd functions are symmetric about the origin. And odd functions have this property here. F of negative x equals negative f of x. And then once again, let's go through a very simple odd function. So the example here is f of x equals x cubed. So to test to see if something is odd, I'm going to use the same test. I want to evaluate f of negative x. Okay, so in this case, if I do that, I get negative x quantity cubed. We know that a negative cubed is still a negative, so I could write this as negative x cubed, right? So this is the negative of our original function. So this is negative f of x, right? So f of negative x equals negative f of x in this case. And that's what happens when you have an odd function, algebraically. Now, what does an odd function look like on a graph? Well, let me make a sketch of x cubed. So it looks something like this, roughly. Okay, so this is the metric about the origin, and this is a little bit harder to see than symmetry about the y-axis. One way that some people like to think about it is if you turn the graph upside down, it would look the same, but basically you're looking for reflection through that origin. Okay, so that's just a quick review of even and odd functions. Now we want to apply this to our function and see if our function is even or odd. So why is this helpful? Well, if our function is even or odd, we can use that symmetry to help us graph it. Okay, so let's check our function then. All right, so remember our function is f of x equals 2x squared plus 3 over x minus 1 times x plus 1. For this part of the problem, I'm actually going to rewrite this function as 2x squared plus 3 over x squared minus 1. It's just going to make the algebra a little bit easier because we won't have those two x's to deal with in the denominator. Okay, so how do I check if something's even or odd? Oh, well, in either case, algebraically what I'm doing is I'm evaluating f of negative x. And I want to see what that gets me in terms of the original function. Okay, so let's go ahead and evaluate f of negative x. So I'm just plugging in negative x to the function. So I get 2 times negative x quantity squared plus 3 over, in the denominator, negative x quantity squared minus 1. Okay, so if I simplify that then, once again, a negative squared is a positive, so this becomes 2x squared plus 3 over x squared minus 1. So what's that? That's the original function, right? So I've just shown that f of negative x equals f of x. So this tells me f of x is even. Or we could also say equivalently, f of x has y-axis symmetry. So when we get to the point where we graph our function, it should be symmetric over that y-axis. So in general, a function can be even or odd, but it can also be neither. A function doesn't have to have either one of these symmetries. All right, moving on to step 3. Step 3 is to calculate the first and second derivatives. And we want to calculate these derivatives because we're going to use them in the subsequent steps to find increasing, decreasing, concavity, extrema, and inflection points. All right, so here's our function. And in this case, to take the derivative, we're going to have to use the quotient rule, right? Because this is a rational function. So let's just go ahead and get started on that. I'm going to start with the first derivative, of course. So quotient rule says bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. Okay, so let's finish taking those derivatives in the numerator there. So we've got x squared minus 1. The derivative of 2x squared plus 3 would be 4x minus 2x squared plus 3 times the derivative of x squared minus 1, which is 2x. And I still have my x squared minus 1 squared in the denominator. Now we want to go ahead and clean up that numerator. And by that I mean basically multiply everything out in recombined terms. Because we might have things that go away, and it's going to be a lot easier to take that second derivative if the first derivative is in the simplest form. So let's see what we get in the numerator. Okay, so if I distribute that 4x, I'm going to get 4x squared minus 4x. Okay, so then I have minus this entire quantity. And if I distribute the 2x, that's going to give me 4x squared, so minus 4x squared. And then minus 6x. Okay, and x squared minus 1 quantity squared in the denominator. So I see that my 4x squareds go away. So that's pretty nice. So on the top, I'm just left with negative 10x over x squared minus 1 quantity squared. And this is my first derivative. I'll be using this a lot in the next few steps. Okay, so now that we have the first derivative, we can use that to find the second derivative. So the second derivative is just the derivative of the first derivative. And once again, we're going to have to use the quotient rule. Okay, so what do we have? Bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. Now in this case, it's x squared minus 1 squared squared. So remember, when you have a power raised to a power, you multiply those powers together. So this is going to become x squared minus 1 to the 4th once I square it. Okay, so let's work on taking those derivatives in the numerator. So this is going to give me x squared minus 1 quantity squared times the derivative of negative 10x, which is negative 10, minus negative 10x. Okay, so now we want to take the derivative of x squared minus 1 squared. Okay, so I need to remember to use a chain rule on this part. I'm going to bring that 2 down. Okay, so I'm using the power rule. I bring the 2 down, and then what's left is raised to the first power. But then I have to remember to multiply by the derivative of the inner function. So that's going to be times a 2x, right? The derivative of x squared minus 1 is 2x. Okay, and then the denominator is just the same. X squared minus 1 to the 4th. All right, so once again, we want to clean this up a little bit because it might simplify to be something really nice. And we're going to have to work with this in subsequent steps, so we want it to be friendly if possible. Okay, so how are we going to clean this up? Well, usually you just want to multiply everything out and then combine terms if possible. If I look at this, though, I see that there's at least an x squared minus 1 in every term, right? So both my terms on top have an x squared minus 1, at least one factor, and then I've got these x squared minus 1s on the bottom. So I can cancel out one factor of x squared minus 1 from every term, which is pretty convenient, right? So in that second term on the top there, it's just going to go away. And the first term on the top, this is just going to be raised to the first power now. And in the bottom, this will now be raised to the 3rd power. Okay, so that simplifies it a lot. Right now I have x squared minus 1 times negative 10 minus, okay, so let me go ahead and multiply all these terms together. I have negative 10x times 2 times 2x. Okay, so that's going to be negative 40x squared. And that's over x squared minus 1 quantity cubed. Okay, so let's see, let's keep working. I'm going to distribute that negative 10. So that's negative 10x squared plus 10 plus 40x squared on top. So in the end, that gives me 30x squared plus 10 over x squared minus 1 quantity cubed. I could also write that as 10 times the quantity 3x squared plus 1 over x squared minus 1 quantity cubed. And remember, this was the second derivative. And we'll use this a lot also in the next few steps. In step 4, we want to find the critical points and possible inflection points. So just as a quick review, critical points are the points where the derivative equals 0 or the derivative does not exist. And these are the possible local max and mins of the function. That's why we're interested in them. And then the possible inflection points, those are kind of like the critical points, but with the second derivative. Those are the places where the derivative equals 0 or the derivative does not exist. And of course, we're interested in them because they are possible inflection points, places where the concavity might change. Okay, so let's start with the first derivative. So the first derivative we found to be, if I scroll up here, negative 10x over the quantity x squared minus 1 squared. All right, so how do we find the critical points? So first, let's think about the points where f prime of x does not exist. Okay, so I can also write this as f prime of x equals negative 10x over x plus 1, x minus 1 quantity squared in the denominator if I just factor that back how it was originally. In general, a rational function like this does not exist when its denominator equals 0. So we can just take that denominator and set it equal to 0. Okay, so we end up with x plus 1, x minus 1 equals 0. So we get solutions of x equals 1 and x equals negative 1. Okay, so let's think about what that means. So in the past, I've always encouraged you to, whenever you find a critical point, just think about whether it's in the domain of the original function. Now in this case, if we scroll back up to our original function, it had this x minus 1, x plus 1 in the denominator, right? So these are not actually in the domain of the original function. So they're not really critical points in the sense that, you know, they're points on the graph of the function. These are not going to be local extrema, right? Because the function doesn't even exist there. But we still want to keep them in mind, right? They're important points for the function, and maybe the derivative does change sign there. So we'll just keep these points in mind for now, even though they're not actually in the domain of the original function. All right, so what about possible inflection points? Okay, so this was for the first derivative. Now let's think about the second derivative, which was 10 times the quantity 3x squared plus 1 over x squared minus 1 quantity cubed. Okay, so I just realized that I completely forgot that we also need to find the places where f prime of x equals 0. Sorry about that. Right, to complete this first part, we need to finish finding the critical points. So let's think about quickly where the derivative equals 0. So in general, remember a fraction equals 0 when its numerator equals 0. So this is going to be when negative 10x equals 0, which gives me a solution of x equals 0. Okay, now we can move on to the second derivative. All right, so once again, I'm looking for the same things here. I'm looking for where f double prime of x does not exist, and then I'll look for where it equals 0. Okay, so once again, we've got a rational function here, and it's going to not exist when the denominator equals 0. So x squared minus 1 quantity cubed equals 0, which gives x squared minus 1 equals 0, and we already factored this, right? It was x plus 1, x minus 1 equals 0, so I get the same solutions. X equals 1 and x equals negative 1. And same deal here, right? These are not actually in the domain of the original function, so we know they're not actually going to be inflection points. But still, the second derivative could change signs there, so we'll keep those points in mind. Now, what about places where f double prime of x equals 0? Okay, so once again, that's going to happen if the numerator equals 0. So I'm now solving this equation. Well, I can divide both sides by 10 and get 3x squared plus 1 equals 0, which give me 3x squared equals negative 1, which would give me x squared equals negative 1/3. But does that have any solutions? It doesn't, because a squared number can never be negative. So this has no solutions. So there are no points where the second derivative equals 0. Okay, so we have all our important points here, our points where the behavior of the function could change. And we'll use these in the next step when we search for local extrema or inflection points. Step 5 in the graphing process is to find the intervals where the function is increasing and decreasing, and then also the intervals where it's concave up, concave down. So to do this, we're going to use the derivatives and the critical values we found in the previous step. So let's start with intervals of increase and decrease. Okay, so usually my favorite way to do this is to set up a number line. So in this case, I want to put my important x values on there. So these are going to be the x values that I had found in step 4. Okay, so increasing and decreasing information comes from the first derivative, right? So what did I find for the first derivative? Well, I found that 1, -1, and 0, or places where the derivative might change signs. Okay, so let me put those on my number line. So -1, 1, and 0. Okay, so those are my x values, and what I want to actually look at now is the sign of the derivative on each of the intervals of my number line here. So the first derivative was -10x over x squared minus 1 quantity squared. Okay, so once again, I'm just concerned with the sign of the derivative, not what it actually is. So let's start testing values. So my first interval here, I'm going to test f of -2. Okay, so if I look over here at my derivative, -2 is going to give me a positive on top, and that denominator is squared, so it's always going to be positive. Okay, so this interval, the derivative is positive. Okay, and then let's see, for the next interval, oh goodness, I wrote these in the wrong order. Sorry about that. It should be 0 and then 1. Makes a lot more sense. Okay, so let's see, I should choose something like -1/2 here. Okay, so if I look at my derivative, once again, that's going to give me a positive on the top, right? Negative times a negative is a positive, and then the bottom's always positive. So here I get a positive again. Okay, and my next interval, I could pick +1/2. Well, that's going to give me a negative on the top, but still a positive on the bottom, so negative overall. And then I could choose 2, and that's going to also give me a negative on the top, positive on the bottom, negative overall. All right, so here's our chart showing the signs of the derivative on different intervals. So let's take that information and actually write out where the function is increasing, the intervals, and where the function is decreasing. All right, increasing. Well, it's increasing where the derivative is positive. So I'm going to write that as -∞ to -1 union -1 to 0. So why did I write it like that? Why did I separate that into two intervals like that? Well, remember, -1 actually isn't in the domain of the function. So the function can't be increasing at a place where it doesn't exist. So that's why I skipped over -1 in my interval. So it's increasing from -∞ to -1, and then again from -1 to 0. Okay, what about decreasing? So same sort of situation here. From 0 to 1, union 1 to infinity. And once again, I'm skipping over 1 because my original function doesn't exist at 1, so it can't be decreasing there. Okay, so now we have our intervals of increasing, decreasing. let's now think about concavity. Okay, so our concavity information is going to come from the second derivative, which was, let's see, 10 times 3x squared plus 1 over x squared minus 1 quantity cubed. Okay, so I'm going to set up a number line again in the same way, but I need to remember to use the points that were important from the second derivative. Which I scroll back up here, we found that -1 and 1 were the important points there. Okay, so I just have -1 and 1 on my line, and I'm looking at the sign of the second derivative. Okay, so let's do some test points. Let's see, I'll pick -2. Okay, so let's see, what's that's going to give me? Okay, so here I might have to do a little bit more work. So on the top, that's going to be 10. Okay, so -2 squared is going to give me +4. So that's definitely positive, right, on the top. What about the bottom? Okay, well, -2 squared is 4, minus 1 is 3. 3 cubed is positive. Okay, so I'm positive there. Positive over positive gives me a positive. All right, what about f of 0 for the middle interval? It's always nice when you get to use 0 as a test point. Okay, on the top, that's going to give me 10 times 1, which is definitely positive. But what about on the bottom? It's going to give me 0 minus 1, which is -1 cubed. And -1 cubed is -1. So this bottom is negative. So I have a positive over a negative, which gives me a negative overall. Okay, and then for my final interval, I could pick 2. So on the top, that's definitely going to be positive, right? 10 times some positive things, positive. What about on the bottom? Well, I have 2 squared minus 1, so that's 3 cubed, which is positive. Okay, so I get a positive overall. Okay, so now I can actually write down my intervals where it's concave up, concave down. Okay, so concave up and concave down. All right, so concave up happens where the second derivative is positive. So in this case, that's going to be -infinity to -1, and also from 1 to infinity. And then concave down is where the second derivative is negative. So that happens from -1 to 1. All right, so we found our intervals of increasing, decreasing, and intervals of concave up and concave down. Step 6 is to find any local maximums or minimums in any inflection points. So to do this, we need to use the information that we found in step 5. Okay, so local maximums or minimums comes from first derivative information. So let's scroll up to our first derivative chart here. Okay, so this is when we were working on intervals of increase and decrease, and we found this chart here. Okay, so local maximums or minimums occur when the derivative changes sign, as long as it's changing sign at a point that actually exists in the domain of the function, right? Okay, so in our case, where does the derivative change signs? Okay, well here, okay, so here I'm increasing, and then after 0 I start to decrease. Okay, so I'm increasing until I get to 0, and then I'm decreasing afterwards. So then it looks like x equals 0 is going to be a local maximum for me. Now I want to just make sure that 0 actually is in the domain of my original function. Okay, so what was my original function? Well, here it was. And yeah, 0 is in the domain. 0 doesn't give me anything funky there. Okay, so it looks like 0 actually is a local max. And there aren't any other locations where the derivative changes sign. Okay, so let's record that information. Okay, so there's a local maximum at x equals 0. Now what's really good to do, so we know there's a local maximum at x equals 0, but let's go ahead and find the y value that's associated with that. That way when we're actually making our graph, we can put the point on there. Okay, so in other words, I want to evaluate what f of 0 is. So let's see, let me write f of x here. F of x was 2x squared plus 3 over x squared minus 1. Okay, so if I plug in 0 there, I get 2 times 0 squared plus 3 over 0 squared minus 1. So 3 over negative 1, which is negative 3. So f of 0 equals 3 is the actual maximum value. So local max value. Okay. So now let's think about any inflection points. Okay, so we found any local extrema. What about any inflection points? So if I scroll back up to my information about concavity, inflection points are places where the concavity changes. Okay, so what do I have here? Well, I have two places where the concavity changes, right? Negative 1 and positive 1, right? It's concave up, and then it's concave down, and then it's concave up. So it looks like negative 1 and 1 are inflection points. Okay, so let me write this down, and then I'll make another point here. So okay, so you'll see there I wrote inflection points with points in quotation marks. So the function, the original function, right, doesn't even exist at negative 1 and 1. So I can't really call them inflection points, right, in the traditional sense of a point. But they are places where the concavity changes, right? So we just might want to keep that in mind. So I'm not going to call them official inflection points, but I'm just going to write this down here. So we just remember that the concavity changes at these points. Okay, and then I'll say the function doesn't actually exist here, but the concavity changes. All right, so now we know where the local extrema are and where the concavity changes. In step 7, we want to find any vertical asymptotes and also find any horizontal asymptotes or other end behavior of the function. So let's start by thinking about the vertical asymptotes. So here I've written the original function, and I've also written the original form at the bottom where it's factored into x plus 1, x minus 1. Okay, so when do vertical asymptotes happen? So kind of the general response to that question is they happen when the denominator equals 0. But just as kind of a condition on that, just be sure that before you look for that, that it's not also a 0 of the numerator. Okay, so in other words, if I look at this denominator here, it looks like negative 1 and 1 are going to be my vertical asymptotes. But I just want to make sure that if I plug in negative 1 or 1, I also don't get a 0 on the top. And that's because vertical asymptotes give the form of a non-zero number over 0. You may remember that from when we talked about limits. But if you have 0 over 0, then that's going to be a whole of some sort. Okay, but in this case, if I plug in 1 or negative 1 to the numerator, I'm not going to get 0 over 0. So x equals 1 and x equals negative 1 are vertical asymptotes. Okay, so we knew before in the very first step we said that, right, the function didn't exist at those points, and they are actually vertical asymptotes. Okay, so what's next? Horizontal asymptotes or end behavior. Okay, so I'll just label this section end behavior. So when we say end behavior, we just mean what happens on the ends of the function, or what happens as the function goes to infinity or to negative infinity. So to figure that out, we're just going to look at the limit of the function at positive and negative infinity. So then I want to know what is the limit as x goes to infinity of my function. Okay, and I'm going to write it as x squared minus 1 here. I know I keep switching forms, but it just kind of depends on which form is easiest for that particular problem. Okay, so I want to take the limit as x goes to infinity of this rational function. Now, back in the, I think maybe section 2.5, we learned a method for doing this, for taking the limit at infinity of a rational function. So if you recall, that method is to divide all the terms by basically the x with the highest degree in the denominator. So in this case, the highest power term in the denominator is x squared. So I'm going to divide every term by x squared. So that's going to look like this. 2x squared over x squared plus 3 over x squared over x squared over x squared minus 1 over x squared. Okay, so you do that, and then you make any simplifications. So in this case, then, this would become in the top 2 plus 3 over x squared, and then in the bottom, 1 minus 1 over x squared. Okay, and then you can think about the limit again, right? Because if I had plugged in infinity before, I would have gotten the form infinity over infinity, which is an indeterminate form that doesn't tell me what the answer actually is, so I do more algebra of some sort. So here I am now. Let's try thinking about the limit again. Okay, so I can think about the limit term by term. So this 3 over x squared term, as x goes to infinity, that denominator is going to get bigger and bigger and bigger, which is going to make the fraction as a whole go to 0. And same with 1 over x squared. That fraction is going to go to 0. So then I'm going to be left with the limit as x goes to infinity of 2 over 1, which just equals 2. Okay, so I just figured out that the limit as x goes to infinity of this function is 2. That tells me I have a horizontal asymptote, right? If the function approaches a line at infinity or negative infinity, we call that a horizontal asymptote. Okay, let's just quickly look at negative infinity as well, just to make sure it's the same. Maybe it's different. Sometimes it's different. I'm going to skip right to this form here, where I've already done the division and simplified. So what about 3 over x squared as x goes to negative infinity? Well, that still goes to 0, right? The bottom's squared, right? So it's still getting bigger and bigger. And even if it wasn't squared, this would still be true. Those terms are still getting smaller and smaller. They're approaching 0. So I get the same answer here of 2. Okay, so we see that we have a horizontal asymptote at y equals 2 on both sides. Okay, so that's how you find end behavior. All right, there's only one more step before we actually graph the function, and that's step 8, find x and y intercepts. So these, of course, are important to graphing the function. You want to know where your x and y intercepts are. Okay, so let's find x-intercepts first. So to find the x-intercepts, you set y equal to 0. Okay, so let's see, my original function again was 2x squared plus 3 over x minus 1, x plus 1. So to find the x-intercepts, I'm just setting that equal to 0 and then solving for x. Okay, so remember, a fraction equals 0 when its numerator equals 0. Okay, so I am left with this. Now we've actually, I think, seen this before. But anyway, if I try to solve for x squared, I get x squared equals negative 3/2. But a square number can't be negative, right? So this has no solutions. So what does that tell me? There are no x-intercepts. So when you graph this function, it should never cross or touch the x-axis at all. Okay, so be careful with that when you actually graph it. What about y-intercepts? Well, y-intercepts are found by setting x equal to 0. Okay, so once again, my function, 2x squared plus 3 over x minus 1, x plus 1. So I want to evaluate f of 0. So plug in 0 for x, and I get 3 on the top, -1 on the bottom. We found this before as well when we found that local maximum. So I find f of 0 equals -3. Or I could also say there's a y-intercept at -3. Okay, so now we have all the pieces of information we need to graph this function. We just have to put them together very carefully. So Elizabeth's going to do that for you in the next video.